Today's forensic chemistry video is going to be on biopolymers and natural fibers and their forensic relevance. So let's get started. So let's talk a little bit about Polymer Basics to review. There's another video on synthetic polymers, and that has quite a bit more about the polymer mechanisms. And then we're going to get into biopolymers. As you can see, we have natural rubber, polysaccharides, and proteins. These are the most forensically relevant polymers for their physical properties. Now, DNA is also a biopolymer, but it's going to be analyzed for the base pair sequences, and so that's not really the physical properties of the polymer, but more the chemical properties and actually the information that's contained in that DNA. And then we'll discuss how these polymers are turned into fibers, and then we'll look at cellulosic fibers and protein, specifically hair. So in terms of polymers in forensic chemistry, there are synthetic and biopolymers and even semi-synthetic. And so this lecture is going to be focused on just the biopolymers and a couple of slides on the semi-synthetic biopolymers or semi-synthetic polymers. So let's get a little bit more information on this huge class of polymers called polysaccharides. But first, let's talk about the polymeric process. So for polymer technology or terminology, we have the monomers, which is the single molecule that is joined together to make the polymer. Poly just meaning many and mono meaning one. So for instance, this particular monomer is called vinyl chloride. And so then if we were to polymerize this, we would have polyvinyl chloride. So we take the name of the monomer and put poly in front of it. There's different ways to join these things together. You can have a random joining of the monomers. Now, what would make up an X or a Y in terms of, say, a vinyl chloride might be whether the chlorine is on the right or the left. So you might have this monomer joined together with the chlorine on the right, and that would be an X version of the monomer. And then if the molecule was rotated around and the chlorine was on the left, that may be a Y. And so it might be right, left, 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 right, right, left, right, left. And so that's random association or random joining of this polymer. You might also have block polymerization, where you have the chlorine on the right 3 times and then on the left 3 times. Now these different kinds of units can join together as well with different types of monomers. So if you have vinyl chloride and some other kind of polymeric monomer, then you might have a vinyl chloride and then maybe a styrene. And it might be vinyl chloride, styrene, 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 vinyl chloride, styrene, etc. Or you can have a whole block, say, of vinyl chloride and then a whole block of styrene. So you polymerize those in a very short or rapid manner, and then you join the 2 solutions of trimers and then join those together to make a block copolymer. Now some monomers have, just by their very nature, the chemical requirement that they be alternating. So one of those examples is here for nylon 6,6. So there's 6 carbons in this diamine. Okay, so we have hexamine or hexane diamine, and that can be joined together with the adipic acid, which has 6 carbons. So it's 4 in the middle, but then these 2 carbonyls on the end. And so these carboxylic acid groups can join together with amine groups with the loss of water. We call that condensation polymerization. And by the chemistry of this having 2 amines, it can only join with the acids. And so this has to be an alternating polymer that has the amine piece and then the acid piece, and then another amine piece and another acid piece. And the way we designate polymers, instead of drawing out some huge structure, we draw the basic repeating unit and we put brackets and we put in. And that's how we would classify the length of the polymer, is by the number density, or how many repeating units it has. Some of these can get up to hundreds of thousands of repeating units. Then you have graft polymerization, where you have a backbone polymer and then these side chains that are linked on. Another very important part of polymeric linkages is how they're joined together. They could be linear, they could be branched, dendritic, where it branches from a central point many times. It makes kind of like a poof. And then also cross-linking is hugely important in terms of the polymer's rigidity. So if you look at these linear polymers nestled together, they might slide past each other. But if you put cross-links in there, they can no longer slide past each other. And so a flexible polymer will turn rigid with the number of cross-links. And in fact, one of the most and earliest known methods for cross-linking is by mixing in sulfur. And sulfur mixed into natural rubber was called vulcanization. So they can mix in sulfur, and that sulfur would react with these chains and cross-link it with this disulfide bond. And so it would hold the polymer together. You could stretch it and basically store energy in that polymer like a spring, and then it would relax and come back. So this is a way to make polymers that still have some plastic, shape bending abilities, but still can come back to their shape and have shape memory. This was a huge development in the production of tires, because vulcanized natural rubber was our first material that we used to make tires, and tires that lasted longer than just a short while. So back in the early days of automobiles, tires were constantly getting flat, and nowadays we can drive thousands of miles without flats. Let's talk a little bit about the physical properties of polymers. And so we have from low temperature to high temperature. This is essentially a generic response of polymers to temperature. So at low temperatures, we either have an amorphous or a crystalline or pseudo-crystalline property of the polymers. But in general, at low temperatures, the polymers will have a fixed shape. And that's either a glassy, amorphous construction, chemical construction inside the polymer, or a crystalline construction inside the polymer, or morphology. But as we raise the temperature, there'll be a certain point where that crystal starts to break apart, and that would be that crystallization temperature. It's kind of like a melting point, but it's not melting. The crystalline rigidity is sort of disappearing, and you get a phase transition into a flexible thermoplastic. The same thing kind of happens here with the glass going to a rubber, which happens at the glass transition temperature. So it goes from a fixed shape to a flexible rubber polymer that still has shape memory, meaning it still has a shape to it, but it's not rigid. So think about Tygon tubing, this plastic tubing. It's flexible, but it still has memory. It's still in the shape of a tube. It still has a standard wall thickness and standard diameter on the inside. It's a tube, but it's flexible. Below that glass transition temperature, it becomes rigid like a glass, and you can shatter it just like glass. And in fact, it has the properties of a glass. You can smack it on the table and it will shatter just like glass tubing if it's below the transition temperature, the glass transition temperature. Now this can have dramatic ramifications. In fact, that's what caused the Challenger space shuttle to blow up, was because the O-rings in the solid rocket boosters were below their glass transition temperature. And the vibration of takeoff allowed those O-rings to leak and spray hot gases onto the main fuel tank. And then that caused a hole or rupture in the main fuel tank, and there was an explosion. So this glass transition temperature is probably the number one property of polymers that can cause the properties to fail if they're in a glassy state when you don't want them to be. You can have fracturing of the polymer. Now, as you raise the temperature, this shape memory, or the fixed shape of the flexible polymer, starts to go away, and you get a gum. Notice there's no line here. There's really no transition temperature. It just, the shape starts to get mushy, if you will. It goes to more of a gum. It can still have a shape, but it doesn't necessarily have shape memory. Think about bubble gum after it's been chewed for a while. It still has a definite shape, but you can push it into a different shape and it doesn't spring back. Or you could think of silly putty. I don't know if you've ever messed with that, but it has a definite shape, but you can change that shape. It has no shape memory. It doesn't try to go back to its previous shape. And then eventually you can raise the temperature to where it will start to flow, and it won't have a definite shape. It will take the shape of its container, which we call the liquid state. And so this is just a rundown of polymers. You notice there's really no fixed melting temperature. There is a glass transition temperature, but there's no melting point. So it just goes gradually from a rubber to a gum to a liquid. So perhaps you didn't know these other types of phases in polymers, this gum state and this rubber state. They're really difficult to define just because they don't have distinct temperatures at which they make this transition from a rubber to a gum. But the main point that you can think about is the shape memory. Whether the polymer, when you push on it, will push back and go back to its original shape, or whether you push on it and it gives and it has no shape memory, it flexes. So it's actually funny that memory foam is exactly the opposite of this. So you push on the memory foam, like the memory foam mattress, you push your hand into it like you see on the commercials, and you remove your hand and it stays there. Okay, that I get their idea that it's remembering the shape of your hand, but in terms of the mattress material, it does not have shape memory. If you press on it and remove your hand and it remembers its original shape, it would spring back to its original shape. And that's what we mean by shape memory, that you squish it and let go and it comes back to its original shape. That's what we mean by shape memory. Let's talk about one of the most common natural biopolymers. This is it may be suspect to call it a biopolymer. It's just a bio-related substance that can be polymerized. And so from tree sap, we get these isoprene monomers, and they have a lot of double bonds. And pretty much any molecule with a double bond can be polymerized. And so we can take this rubber that is extracted from tree sap, add in sulfur, and cross-link it, and make this isoprene rubber or butyl rubber. And it's a very good substance for boots and gloves and scuba masks and so on. It's very inexpensive because it's a natural product. The tree does most of the synthesis. And so we just provide some chemical conditions where it will polymerize and where it will cross-link and have the properties that we want it to have. The other very important biopolymers are polysaccharides. These are carbohydrates. And think about the name, carbohydrate. It's carbon and water joined together. And so this would be the empirical formula for all carbohydrates, which means all sugars, all starches, and all cellulosic materials. They are all carbon and water joined together and just in different numbers of monomers. Now, the monomers are made up of 5, 6, and 7, and 8 membered rings, mostly 6. And so here's this chair form of a carbohydrate, and you can see that it's chiral. We'll look at that in a second. But we have this anomeric carbon that can have the OH be in the axial position or in the equatorial position. And so we have all of the variety of carbohydrate chemistry. I mean, you could be, in fact, I heard a talk one time through the ACS of a scientist who spent his whole career, 35, 40 years of chemistry only on carbohydrate chemistry. He was an expert in carbohydrate chemistry because it's so complex. I mean, you have everything from table sugar to pine trees, and it has pretty much the same structure in terms of the base chemicals. It's a carbon and a water. And so there's different views and forms of these sugars. So here's a glucose unit. We can have the Fischer projection. And notice how you have the different OHs on the right or the left. You can make ring structures. You can have that C6 rotated on the right side or rotated up. If it's rotated up, you have this Hayworth projection. And then you can have the OH be in the up position or in the down position. So here, when you have all of the extra substituents in the equatorial position, you can have the OH pointed out or the OH pointed down, and that small change will make a huge difference in whether this can be polymerized in a form that makes cellulosic fibers or starches or sugars. And we can metabolize starches and sugars very easily in our body. We cannot metabolize the cellulosic materials, and so these are metabolized by enzymes, and so the structure of these biopolymers are very important biochemically. They're also very important when they are placed by the plant into macroscopic structures that we can inspect under a microscope. And so you can just see that the chemistry of carbohydrates is incredibly complex. And most of these will join together with the loss of water. So it's condensation, polymerization. And so you have this OH group on the 1 group interacting with the OH on the 4 carbon, and this water goes away, leaving behind the oxygen linkage. And so that's the 1,4' glycosidic bond. And if they're both in the equatorial position, you have a disaccharide. Up here you have other kinds of, if it's in the axial position and so on, you'll have a different kind of linkage. And so this is all of the different variety of polymers that we see from the polysaccharides. We have starches, which is how we store energy. Materials, which are fibrous materials that are related to wood and cotton fiber and plant cell walls, etc. And then those cellulose related materials that go along with these plant-based polymers like hemicellulose, lignins, pectins, and alcohols. So we're going to focus on these polysaccharides for a little bit. One of those that we see is also glucosamine, and this is a cellulosic material that's been modified with an amide linkage. And so here's the amide right here. And this sets up some directional hydrogen bonding that makes this very rigid. And so this acts as the exoskeleton in insects and arthropods. So you can think about that hard shell on a beetle or a roach. And so if you're taking glucosamine, supposedly it's supposed to be good for your joints and cartilage, but it kind of freaks people out to hear that they're basically eating the ground up insect shell. So hopefully that doesn't cause you to swear off the glucosamine. Now let's think about the starches. This is a very efficient way to store energy, because if you have extra sugar than your body doesn't need at the moment, it can store it in the body, or plants can store it this way. And notice that glycogen versus amylopectin is a more efficient way to store energy, because you have to join these extra starch rings on the ends of these groups. And look how many more ends we have in the glycogen compared to the amylopectin. This one only has 2, 4, 6, 7 ends, and that's the only place that you can easily store in that 1,4' linkage the next saccharide monomer. Whereas look at this one; it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Easily 20, maybe 22 different end groups, and you're going to be able to store energy much faster on this arrangement and retrieve it much faster from this arrangement. Now you can have branching, and this is how that branching occurs. You can have a string of 1,4' bonds, and then you can split off on the 1,6' linkage. And so you can have branching in this, and so the more branched the starch, the more efficient it is in terms of energy storage and energy retrieval for the body. Now if we take these starches and these cellulosic polymers and join them together in a large structure, then you start to get to the lignocellulose complex, or we like to, plant wall structures, stems, woody plant stems, and then even trees. So this is this matrix of cellulose and hemicellulose mixed in with lignin and hemicellulose. And so we have these coniferyl alcohols, and we have the lignins, these complex molecules that go in, and these right here are I'm only showing two of them, like thousands of molecules that are probably the least well characterized substances in these natural fibers. These may in the future, when they're characterized more accurately, have forensic use, but at this point they're just extracted from these different cellulosic fibers whenever we make paper, and it's called tall oil. It's a really dark glue-like substance, and it can be there's a lot of molecules in there that may be useful as solvents. And so right now, that's where I've come across it in my research, is companies that take tall oil from paper plants want to extract some of the substances in there and maybe an inexpensive source of cleaning solvents or processing solvents. Now, another forensic item you may come across is fireproof fabric. And so if you have a cotton fiber, it's very flammable. And we found this out, over time, that clothes can burn quite easily. And so they've explored ways to fireproof clothing. And so they can mix in clay with the cotton fiber, and that clay will heat up in a flame or in a fire situation and create a quick char coating that can act as a barrier to oxygen, so that the clothes will decompose somewhat with this sort of cotton, this fiber or clay catalyst, and create a passive layer that protects the clothing from flame, and from oxygen. So you may find, in forensic analysis, cotton fibers that have other constituents in them other than the dyes, and those constituents may be the fireproofing constituents. Now, you might have dyes, and you can have dyes that are mixed in with the clothing and just can be washed out. And then you might have heard recently, I guess in the last 20 or 30 years, they're actually chemically fixing the dyes to the cotton clothes, and they call those Colorfast fabrics. So they've made a covalent bond of the coloring molecule, of the coloring chromophore molecule to the cellulose fiber. And so this might be this is showing like a triazine dye, so it's using kind of the azo type chromophore with aromatic rings. You have an extended pi cloud. It's going to give you a deep color in the visible region, and yet it's covalently bonded to the cellulosic fibers. So you come along with bleach and so on, and it's not going to remove this dye very easily, and so you can clean these clothes many more cycles than you could with a dye that's just mixed in with the cellulose and could be dissolved away from the cellulose. Now let's look at this process where we take cellulose, which is this R group, and it has an OH bond. It's bristling with OH alcohol groups, and you react it with strong base and carbon disulfide, and you actually put this carbon disulfide onto the cellulosic backbone, and you make this cellulose xanthate or viscose. Now, this is soluble in water, so it can be extruded into solution, and then you can react it with sulfuric acid and make the sulfate salt, and then you can add in water to hydrolyze that bond again, and then make regenerated cellulose. So what you started with, this ROH and CS2, you end up with in the end ROH and CS2. Now, why would this be useful in terms of a chemical process? We basically took cellulose, reacted it with carbon disulfide, and then in the end we got cellulose back in carbon disulfide. So what's happening here? Why would we want to do this? And why would we call this rayon instead of cotton? Well, in the old days, the fibers had to be spun, and they would just be, think about the cotton ball. The fibers were very short, and they were mechanically spun together, and that's what made yarn and thread, and then we could sew and weave with that. But when we go through this process and make this cellulose xanthate, then we can mix those fibers together at the molecular level in solution, and we can extrude that and regenerate it and make rayon fiber, and then those threads can be literally miles long. I mean, they can go onto these spools. They're much stronger because they're entangled at the molecular level, not just at the macro level. And so this is modern textiles was really advanced by these semi-synthetic fibers like rayon. The downside of rayon is that it produces a very smooth fiber, and so then the fabrics don't look like cotton. They look artificial, if you will. They're shiny. And so a lot of times they'll put dulling agents in with the rayon fibers so that they don't look shiny. But if you want shiny fabric, then this is fantastic, because rayon is much more shiny and much more straight weaving than cotton. And so here's an example. Also, you could acetylate those OH groups and make cellulose acetate fibers. And this is a micrograph of cotton fibers, and you can see how coily it is, and it's kind of like a flat fiber that coils around, and it's very curly. And you can react that with acetate, dissolve it in solution, extrude it through some tiny little spinnerets to make straight fibers, and now you have cellulose acetate fibers. Very smooth surface, very uniform, not coily, and can again be stretched and are very strong, much stronger than just straight cotton. Let's talk about paper for a little bit. So we could take wood, either soft or hardwood, chip it up, and then even mix in some recycled paper products. And this again is looks kind of brownish because of those tall oil components. And so this is in the pulping. We would smash it in with sulfuric acid and other kinds of industrial chemicals and create this pulp. Then we bleach it by removing those lignins, and that's again that tall oil that I was talking about. And it's possible that tall oil will have, residual tall oil in the papers and so on may in the future have forensic relevance whenever we more fully characterize it. A strange little function of the EPA's incentive structure for industrial uses of these byproducts is that if this tall oil comes out and it can be burned, it's combustible, is just mixed in with other oil components and burned, you get actually some green energy credits for that, because this is a bioprocess. This is a byproduct, and so instead of doing something chemically useful with the tall oil, like making a solvent or some sort of industrial, there's quite a bit of chemistry in these alcohols. Just doing something crude like burning them at this point is getting green energy credits. So, but selling something to burn, they want that price to be as low as possible. And so the companies that are looking at tall oil are trying to find a higher paying market for this byproduct, because if you could sell it for a solvent and use its solvating properties, then you could sell it for a higher price than just selling it to burn. But anyway, so you remove those lignin compounds, and the paper pulp turns much more white. Then you can beat it and process it into paper. And so this cross section of paper, you have these fibers that are flattened and rolled out. You have moisture in there that holds it all together, and it's a very porous structure. And so that's why paper fibers absorb water so well, because if you think about the cellulose, it's like I said, it's just covered in OH groups, and those will hydrogen bond to other OH groups, and especially water. So you can take these paper substances, make towels out of them, and so on, and they're just great for absorbing water. Let's compare the best methods that we have for making synthetic fibers and compare that to what nature is able to do. And so if you take a carpet fiber or some other kind of microfiber cloth that's a polymer, like a polyethylene microfiber or polyester microfiber, carpet fiber, and you cut it in a cross section, you might find some complex shapes to give it the color they want, or maybe even the bending properties that they want. Sometimes they have multi-component fibers where they'll have like maybe a cheap fiber in the middle, a cheap polymer in the middle surrounded by a more expensive polymer to give it the feel properties that they want or the color properties that they want. And so this would be a dual extrusion fiber. And so the cross section, even though these fibers may have the same external dimension, if you look at it, the cross section under a microscope, you might see some complexity there. Even some other more complex extrusions here. But in terms of our synthetic fibers, this is considered a complex fiber. Compare that to with what nature produces. Here's a naturally produced fiber. This is hair. And you can see all of the cellular structures in hair. It's incredibly complex. Our best technology in terms of multi-core fibers cannot come anywhere close to what nature does with hair. Now there are three main components to hair. There's the medulla, which is the very central piece, the cortex, which is that body in between the medulla and the cuticle, and the cuticle is that outside layer. And these three pieces of a hair will be different depending upon where it came from, the race of the individual even sometimes, and whether it's an animal or a human hair or what type of animal hair it is. And so we can explore these different fibers with microscopy. And so polarized light microscopy is probably the best tool to use for looking at the different kinds of fibers. Like I've shown you pictures already, the difference between acetate, silk, and cotton would be obvious under a microscope. And even like hemp fibers here and bast fibers, milkweed fibers, those are going to be easily distinguishable from cotton fibers or flax. And so this is again a fantastic tool. If you've got fiber evidence, your number one tool for analyzing that would be photography in the microscope. Now hair is also a very important forensic indicator because it's almost everywhere. When you think about pet hair, and so, if the suspect has a pet, they're going to have pet hair on their clothing. And if let's say it's a homicide and the victim does not have any pets at all, and you find pet hair at the scene, well, this could be an indicator of the suspect. Now, if it's an orange tabby cat and that's a ubiquitous tabby cat, it may not be too isolating. But what if this suspect is, maybe he has goats, okay, and you find goat hair on the suspect, and you find goat hair in the victim's house. This may be much more forensically relevant. You have cat hair. Notice a really dark medulla and a really dark cortex, and the cuticle is light under cross polarization, and that's very different than antelope hair or deer hair or a rabbit wool. Notice the rabbit wool has a very complex medulla, and you see these structures inside the center of the fiber. Same with alpaca. So a lot of times the pigmentation of the hair is in the medulla. Other times it's in the cuticle. And so this will tell you quite a bit about the different types of hair. And this is a great tool, microscopy, for analyzing hair and fiber evidence. I encourage you to go to this Olympus microscope gallery. This is a great website of images. And so let's just go there quickly. And so here's the Olympus microscopy resource, and down here it says digital image galleries. So you click that, and you can look at all of these different kinds of images that were taken on, of course, on Olympus microscopes. And so let's look at, I think this was the polarized light microscope gallery that I used to find the hair. Chemical crystals will also give different types of micrographs that may be forensically relevant. And so look at all of these different kinds of chemical substances. Now, some of them may be difficult to tell the difference between, like, anthranilic acid and maybe folic acid, but look at biotin. I mean, this is a very unique image that comes from all the different crystals of biotin. And so there may be some forensically relevant imagery that you could use. If you have some standards and you have some suspected materials, you can look at those under cross-polarized light microscopy, and you might be able to see some characteristic crystal signatures. Now, how do you get these crystals to grow? It's really pretty easy. If you dissolve the substance in methanol or some suitable solvent and put that on a microscope side and let the solvent evaporate slowly, and I'm saying just slowly, like you just wave your hand over it and let the air take the solvent away, then these substances will crystallize on the glass slide. And then you can look at them under the microscope. And you can see all of these different substances have some different properties under polarized light analysis. Here's the different fibers. Some of these are synthetic, some of these are natural. Some are semi-synthetic, but you can see the different types of behaviors under polarized light microscopy. And then here are the different hairs. So we have, very specific human hair here. So you can see the pigmentation in the medulla, which is different than leopard hair or mink hair or mole hair. Okay, possum, raccoon, and rabbit. Here, look at the skunk hair. You see the medulla is filled with pigmentation. Then you have the cuticle and the cortex. Here's different rocks and minerals. And so maybe a little bit more difficult to get some of these substances. So you may have to do them under reflection, but you can still do polarized light microscopy under reflection. And again, some quite distinct patterns. You may not be able to determine between, say, these two substances, but you could tell the difference between these two substances in green slate or glauconite or garnet. And so hopefully that has given you a good feel for the forensic evidence that you might find in terms of natural fibers. The take-home lesson would be that natural fibers and biogenerated fibers like hair can be enormously more complex than any kind of synthetic fiber that we could make. And so looking at a cross-section of the fiber is important, and then also looking at the structure, the overall structure of the fiber using cross-polarized light in a microscope. Okay, have a great day.